Chapter 15 Metalworking. We referred in the last chapter to the fact that metal, when it came from the melting and puddling furnace, was formerly rolled into sheets, but when the manufacturers and consumers got these sheets, then came the severe, laborious work by hand of cutting, hammering, boring, shaping and fitting the parts for use, and securing them in place. It is one of the glories of this century that metalworking tools and machinery have been invented that take the metal from its inception, mold and adapt it to man's will in every situation, with an infinite saving of time and labor, and with a perfection and uniformity of operation, entirely impossible by hand. Although the tools for boring holes in wood, such as the gimlet, auger, and the lathe to hold, turn and guide the article to be operated on by the tool, are common in some respects with those for drilling and turning metal, yet the adaptation to use with metal constitutes a class of metalworking appliances distinct in themselves, and with some exceptions not interchangeable with woodworking utensils. The metalworking tools and machines forming the subject of this chapter are not those which from time immemorial have been used to pierce, hammer, cut, and shape metals, directed by the eye and hand of man, but rather those invented to take the place of the hand and eye, and be operated by other powers. It needs other than manual power to subdue the metals to the present wants of man, and until those modern motor powers, such as steam, compressed air, gas and electricity, and modern hydraulic machinery, were developed, automatic machine tools to any extent were not invented. So, too, the tools that are designed to operate on hard metal should themselves be of the best metal, and until modern inventors rediscovered the art of making cast steel, such tools were not obtainable. The monuments and records of ancient and departed races show that it was known by them how to bore holes in wood, stone and glass, by some sharp instruments turned by hand, or it may be by leather cords, as a top is turned. The lathe, a machine to hold an object, and at the same time revolve it while it is formed by the hand, or cut by a tool, is as old as the art of pottery, and is illustrated in the oldest Egyptian monuments, in which the god Ptah is shown in the act of molding man upon the throwing wheel. It is a device as necessary to the industrial growth of man as the axe or the spade. Its use by the Egyptians appears to have been confined to pottery, but the ancient Greeks, Chinese, Africans, and Hindus used lathes for woodworking, in which the work was suspended on horizontal supports and adapted to be rotated by means of a rope and treadle and a spring bar, impelled by the operator as he held the cutting tool on the object. Joseph Holtzapfel, in his learned work on turning and mechanical manipulation, gives a list of old publications describing lathes for turning both wood and metal. Among these is Hartmann Schaffer's book published at Frankfurt in 1548. A lathe on which was formed wood screws is described in a work of Jacques Besson, published at Lyons, France, in 1582. It is stated that there is on exhibition in the Abbott Museum of the Historical Society, New York, a bronze drinking vessel, 5 inches in diameter, that was exhumed from an ancient tomb in Thebes, and which bears evidence of having been turned on a lathe. It is thought by those skilled in the art that it was not possible to have constructed the works of metal in Solomon's temple without a turning lathe. One of the earliest published descriptions of a metal turning lathe in its leading features is that found in a book published in London in 1677-83 by Joseph Moxon, hydographer to King Charles II, entitled Mechanical Exercises, or the Doctrine of Handiworks. He therein also described a machine for planing metal. Although there is some evidence that these inventions of the learned gentleman were made and put to some use, yet they were soon forgotten and were not revived until a century later, when, as before intimated, the steam engine had been invented and furnished the power for working them. Woodworking implements in which the cutting tool was carried by a sliding block were described in the English patents of General Sir Samuel Bentham and Joseph Bramah in 1793-94. But until this century, and fairly within its borders, man was content generally to use the metal lathe simply as a holding and turning support, while he, with such skill and strength as he could command, and with an expenditure of time, labor and patience truly marvelous, held and guided with his hands the cutting tool with which the required form was made upon or from the slowly turning object before him. The contrivance which was to take the place of the hand and eye of man in holding, applying, directing and impelling a cutting tool to the surface of the metal work was the slide rest. In its modern successful automatic form, Henry Maudsley, an engineer in London, is claimed to be the first inventor in the early part of the century. The leading feature of his form of this device consists of an iron block which constitutes the rest, cut with grooves so as to adapt it to slide upon its iron supports, means to secure the cutting tool solidly to this block, and two screw handles, one to adjust the tool towards and against the object to be cut in the lathe, and the other to slide the rest and tool lengthwise as the work progresses, which latter motion may be given by the hand, or effected automatically by a connection of the screw handle of the slide and the rotating object on the lathe. A vast variety of inventions and operations have been affected by changes in these main features. Of the value of this invention, Nasmyth, a devoted pupil of Maudsley and himself an eminent engineer and inventor, thus writes: "It was this holding of a tool by means of an iron hand, and constraining it to move along the surface of the work in so certain a manner, and with such definite and precise motion, which formed the great era in the history of mechanics, inasmuch as we thenceforward became possessed, by its means, of the power of operating alike on the most ponderous or delicate pieces of machinery, with a degree of minute precision, of which language cannot convey an adequate idea. And in many cases we have, through its agency, equal facility in carrying on the most perfect workmanship in the interior parts of certain machines, where neither the hand nor the eye can reach, and nevertheless, we can give to these parts their required form with a degree of accuracy, as if we had the power of transforming ourselves into pygmy workmen, and so apply our labor to the innermost holes and corners of our machinery." The scope of the lathe, slide rest and operating tool, by its adaptation to cut out from a vast roll of steel a ponderous gun, or by a change in the size of parts to operate in cutting or drilling the most delicate portions of that most delicate of all mechanisms, a watch, reminds one of that other marvel of mechanical adaptation, the steam hammer, which makes the earth tremble with its mighty blows upon a heated mass of iron, or lightly taps and cracks the soft-shelled nut, without the slightest touch of violence upon its enclosed and fragile fruit. The adaptation of the lathe and slide to woodworking tools will be referred to in the chapter relating to woodworking. Following the invention of the lathe and the slide rest, came the metal planing machines. It is stated in Buchanan's Practical Essays, published in 1841, that a French engineer in 1751, in constructing the Marly Water Works on the Seine in France, employed a machine for planing out the wrought iron pump barrels used in that work, and this is thought to be the first instance in which iron was reduced to a plain surface without chipping or filing. But it needed the invention of the slide rest and its application to metal turning lathes to suggest and render successful metal planing machines. These were supplied in England from 1811 to 1840 by the genius of Bramah, Clement, Fox, Roberts, Rennie, Whitworth, Fletcher, and a few others. When it is considered how many different forms are essential to the completion of metal machines of every description, the usefulness of machinery that will produce them with the greatest accuracy and dispatch can be imagined. The many modifications of the planing machine have names that indicate to the workman the purpose for which they are adapted, as the jack, a small portable machine, quick and handy; the Jim Crow, a machine for planing both ways by reversal of the movement of the bed, and it gets its name because it can wheel about and turn about and do just so; the key groove machine, the milling machine with a serrated faced cutter bar, shaping machine and shaping bar, slotting machine, crank planer, screw cutting, carwheel turning, bolt and nut screwing, etc. As to the mutual evolution and important results of these combined inventions, the slide rest and the planer, we again quote Nasmyth: "The first planing machine enabled us to produce the second still better, and that a better still, and then slide rests of the most perfect kind, came streaming forth from them, and they again assisted in making better still, so that in a very short time a most important branch of engineering business, namely, tool-making, arose, which had its existence not merely owing to the pre-existing demand for such tools, but in fact raised a demand of its own creating." One has only to go into any of these vast establishments which have sprung up in the last 30 years to find that 9/10 of all the fine mechanisms in use and in process of production are through the agency, more or less direct, of the slide rest and planing machine. Springing out of these inventions, as from a fruitful soil, came the metal boring machines, one class for turning the outside of cylinders to make them true, and another class for boring and drilling holes through solid metal plates. The principle of the lathe was applied to those machines in which the shaft carrying the cutting or boring tool was held either in a vertical or in a horizontal position. Now flowed forth, as from some Vulcan's titanic workshop, machines for making bolts, nuts, rivets, screws, chains, staples, car wheels, shafts, etc., and other machines for applying them to the objects with which they were to be used. The progress of screw making had been such that in 1840, by the machines then in use for cutting, slotting, shaving, threading, and heading, 20 men and boys were enabled to manufacture 20,000 screws in a day. 35 years later, 2 girls tending 2 machines were enabled to manufacture 240,000 screws a day. Since then the process has proceeded at even a greater rate. So great is the consumption of screws that it would be utterly impossible to supply the demand by the processes in vogue 60 years ago. In England's first great international fair, in 1851, a new world of metallurgical products, implements, processes, and metalworking tools were among the grand results of the half-century's inventions which were exhibited to the assembled nations. The leading exhibitor in the line of self-acting lathes, planing, slotting, drilling and boring machines was J. Whitworth and Company, of Manchester, England. Here were for the first time revealed in a compact form those machines which shaped metal as wood alone had been previously shaped. But another quarter of a century brought still grander results, which were displayed at the Centennial Exhibition at Philadelphia in 1876. As J. Whitworth and Company were the leading exhibitors of London in 1851, so were William Sellers and Company, of Philadelphia, the leading exhibitors in the 1876 exhibition. As showing the progress of the century, the official report, made in this class by citizens of other countries than America, set forth that this exhibit of the latter company, in extent and value, in extraordinary variety and originality, was probably without parallel in the past history of international exhibitions. Language seemed to be inadequate to enable the committee to describe satisfactorily the extreme refinement in every detail, the superior quality of material and workmanship, the mathematical accuracy, the beautiful outlines, the perfection in strength and form, and the scientific skill displayed in the remarkable assemblage of this class of machinery at that exhibition. An exhibit on that occasion made by Messrs. Hoopes and Townsend of Philadelphia attracted great attention by the fact that the doctrine of the flow of solid metal, so well expounded by that eminent French scientist, M. Tresca, was therein well illustrated. It consisted of a large collection of bolts and screws which had been cold punched, as well as of elevator and carrier chains, the links of which had been so punched. This punching of the cold metal without cutting, boring, drilling, hammering, or otherwise shaping the metal, was indeed a revelation. So also at this exhibition was a finer collection of machine-made horseshoes than had ever previously been presented to the world. A better and more intelligent and refined treatment of that noble animal, the horse, and especially in the care of his feet, had sprung up during the last half-century, conspicuously advocated by Mr. Fleming in England, and followed promptly in America and elsewhere. Within the last 40 years, nearly 200 patents have been taken out in the United States alone for machines for making horseshoes. Prejudices, jealousies and objections of all kinds were raised at first against the machine-made horseshoe, as well as the horseshoe nail, but the horses have won, and the blacksmiths have been benefited despite their early objections. The smiths make larger incomes in buying and applying the machine-made shoes. The shoes are not only hammered into shape on the machine, but there are machines for stamping them out from metal at a single blow, for compressing several thicknesses of raw hide and molding them in a steel mold, producing a light, elastic shoe, and without calks, furnishing shoes for defective hoofs, flexible shoes for the relief and cure of contracted or flat feet, shoes formed with a joint at the toe, and light, hard shoes made of aluminium. Tube making. Instead of heating strips of metal and welding the edges together, tubes may now be made seamless by rolling the heated metal around a solid heated rod, or by placing a hot ingot in a die and forcing a mandrel through the ingot. And as to tube and metal bending, there are wonderful machines which bend sheets of metal into great tubes, funnels, ship masts and cylinders. Welding. As to welding, the seams, instead of being hammered, are now formed by melting and condensing the edges, or adjoining parts, by the electric current. Annealing and tempering. Steel wire and plates are now tempered and annealed by electricity. It is found that they can be heated to a high temperature more quickly and evenly by the electric current passed through them than by combustion, and the process is much used in making clock and watch springs. One way of hardening plates, especially armor plates, by what is called the Harvey's process, is by embedding the face of the plate in carbon, protecting the back and sides with sand, heating to about the melting point of cast iron, and then hardening the face by chilling, or otherwise. Coating with metal. Although covering metal with metal has been practiced from the earliest times, accomplished by heating and hammering, it was not until this century that electroplating and plating by chemical processes, as by dipping the metal into certain chemical solutions, and by the use of automatic machinery, were adopted. It was in the early part of the century that Volta discovered that in the voltaic battery, certain metallic salts were reduced to their elements and deposited at the negative pole, and that Wollaston demonstrated how a silver plate in bath of sulfate of copper, through which a current was passed, became covered with copper. Then in 1838, Spencer applied these principles in making casts, and Jacobi in Russia, shortly after Electro gilded a dome of a cathedral in St. Petersburg. Space will not permit the enumeration of the vast variety of processes and machines for coating and gilding that have since followed. Metal founding. The treatment of metal after it flows from the furnaces, or is poured from the crucibles into molds, by the operations of facing, drying, covering, casting and stripping, has given rise to a multitude of machines and methods for casting a great variety of objects. The most interesting inventions in this class have for their object the chilling, or chill hardening, of the outer surfaces of articles which are subject to the most and hardest wear, as axle boxes, hammers, anvils, etc., which is effected by exposing the red-hot metal to a blast of cold air, or by introducing a piece of iron into a mold containing the molten metal. In casting steel ingots, in order to produce a uniform compact structure, Gears of England invented soaking pits of sand, into which the ingot from the mold is placed and then covered, so that the heat radiating outward reheats the exterior, and the ingot is then rolled without reheating. Sheet metal wear. Important improvements have been made in this line. Wonderful machines have been made which, receiving within them a piece of flat metal, will, by a single blow of a plunger and a die, stamp out a metal can or box with tightly closed seams, and all ready for the cover, which is made in another similar machine, or by which an endless chain of cans are carried into a machine, and they're automatically soldered at their seams, and another which solders the heads on filled cans as fast as they can be fed into the machine. Metal personal wear. Buckles, clasps, hooks and eyelets, shanked buttons, and similar objects are now stamped up and out, without more manual labor than is necessary to supply the machines with the metal, and to take care of the completed articles. Wire working. Not only unsightly but useful barbed wire fences, and the most ornamental wire work and netting for many purposes, such as fences, screens, cages, etc., are now made by ingenious machines, and not by hand tools. In stepping into one of the great modern works where varied industries are carried on under one general management, one cannot help realizing the vast difference between old systems and the new. In one portion of the establishment the crude ores are received and smelted and treated, with a small force and with ease, until the polished metal is complete and ready for manipulation in the manufacture of 100 different objects. In another part ponderous or smaller lathes and planing machines are turning forth many varied forms. In quiet corners the boring, drilling, and riveting machines are doing their work without the clang of hammers. In another, an apparently young student is conducting the scientific operation of coating or gilding metals. In another, girls may be seen with light machines, stamping, or burnishing, or assembling the different parts of finished metal ware. And the motive power of all this is the silent but all-powerful electric current received from the smooth-running dynamo giant, who works with vast but unseen energy in a den by himself, not a smoky or a dingy den, but light, clean, polished, and beautiful as the workshop of a god.